Thank you very much for joining us this morning. We're going to get started in just about two to 3 minutes, maybe a little bit longer. We may give people a little more time to register, but we'll be getting started shortly. Thank you. Hi, George. You want to say a couple words just to make sure your microphone is working?
Sure thing. I hope you can hear this.
Sounds great. Thank you.
Great.
Hi, Todd. Can you say a couple words just to make sure your microphone is working?
Yeah, can you hear me?
I can hear you. Thank you. We're going to go ahead and get started in probably about a minute.
Okay, great.
Good morning, good afternoon, or good evening, depending on where you're located. Thank you so much for joining us today. I'm going to go ahead and get started. We'll start with a few introductory slides, and then we'll move on to the meat of the program. Let me go ahead and share my screen. So, first off, congratulations on being admitted to USC. Our admission process is extremely competitive, so you're definitely part of a very small group that's been admitted to the University of Southern California. So again, congratulations on your admission to USC and our MS in Quantum Information Science. So welcome to the University of Southern California. Let's start with some considerations as to when you're deciding which school. The assumption is you've been admitted both to USC and other top schools. So a lot of what you're thinking about right now is exactly which of those schools is going to be the best fit for you. So some things to think about. One of them obviously is your career and your academic goals after you complete your graduate studies. As far as academic goals go, you'll want to be looking at whether or not the program you've been admitted to has all of the courses and the sort of research you're interested in, things like that. For your career, one thing to keep in mind is that every university's reach as far as companies and such tends to get stronger as it gets closer to the university. So think about the location that you want to be after you graduate. So if you want to be on the West Coast, then obviously USC is a great choice, as are other schools. Um, think about whether or not you're interested in things like, long summers, warm weather, whether you prefer four seasons, how comfortable you are with snow. All these things do affect you. Those things are not a major consideration for master's programs, simply because you're going to complete the program in 1.5 to 2 years in all likelihood. Some other things to think about is the strength of the alumni network. This is one of the things that you're really going to want to look at, because networking is one of the most important things you're going to get out of your university education, other than the academic goals, because your network is basically going to be one of the cores of finding jobs and things like that. I mentioned research a little earlier, but obviously if you are interested in doing research, you will want to know what sort of research opportunities are available. So location, we are in the heart of Los Angeles, which is a global hub for innovation, for research. As you might guess, we're a major hub for a lot of different industries, including aerospace, astronautics, biomedical engineering, obviously the entertainment industry. So a lot of different industries. We're also the home of Silicon Beach, which is basically one of the fastest growing entrepreneurial tech hubs in the world. You can kind of see just some of the companies that have got outlets here. So Bird Scooters, Twitter, Hulu, Amazon, the Jet Propulsion Laboratory in Pasadena, Google, YouTube, all of these groups have major presences in Los Angeles. On the other hand, if you're thinking about just sort of like, what is Los Angeles like? We are obviously a major urban hub with a lot of diversity. We have a lot of natural beauty. Everything from beaches to mountains, deserts. Los Angeles is probably one of the only cities where you could conceivably ski, surf, hike in the desert, and go clubbing all in the same 24-hour period, if you've got the energy to do so. One of the things you're definitely going to be interested in is basically, how is USC going to help you find a job, or if you're interested in academics, continuing on to a PhD program. The Viterbi School of Engineering does have its own career services group. It's called the Viterbi Career Gateway. And although a lot of people tend to think of career services as just having career fairs or expos, and our Viterbi School does have 2 of those, it's actually really important to know that a lot more than that happens. We have signature events where you can network with industry professionals. You can do internships. We have a lot of workshops on things like interviewing skills, resume writing, all that sort of things. We have job and internship toolkits where you can explore the online resources to further your development. If you're an international student, we have a lot of international students, so we have a real strength in career resources for our international students, including a very robust CPT and OPT internship program. And then finally, career exploration. You can dig a lot deeper into potential career opportunities in various industries. So to give you an idea, it's just some of the sort of events they have. And this is an example of actually when these companies come to USC specifically to talk to our students outside of a career fair. We have mock interviews, we have various types of boot camps, and Viterbi Trek is one that's really kind of cool because it's basically a field trip where we take students to company campuses to sort of visit the companies basically in their native environment. We also do have a mentorship program, simply because we know, especially if you're not local to California and Los Angeles, or are an international student, it can be challenging, basically fitting in and kind of getting set up when you first arrive at USC. So our mentorship program is literally there to help you on your journey at USC. New students are basically paired with our current Viterbi graduate students. We try to match academic departments and degree levels. In other words, if you're a QIS student, master's QIS student, we will try to match you with someone in that same area, or at least within our ECE department. One really important thing, fall 2023 deadline. All of you have been admitted. If you're not sure as to the last day you can accept your admission, check your statement of intent. Just below the program name is going to be the last date you have in order to accept your admission at USC. Most of you will either see a deadline of April 15th or May 1st. One of the reasons that we suggest that you submit the statement of intent as soon as you have decided that you are going to come to USC is that you have access to a lot of things like pre-orientation resources. Once you accept your admission, you can request membership in the mentorship program. You can participate in academic webinars, and especially if you want to live in USC-owned housing, you can explore housing options at USC and enter the USC housing lottery. There is plenty of housing for USC students, just not all of it is actually owned by USC. So that's basically a quick overview. So I'm going to stop the share and introduce our professors. Professor Todd Brunn, who's with our Viterbi School of Engineering, and Professor George Ingersoll, who is with our Dornsife School of Letters, Arts, and Sciences. And I'm going to let them take over and talk a bit more about the program.
Thank you very much. So I'm going to just give a brief summary of the MSQIS program and what its intent is, what the requirements are, and then we'll do a Q&A afterwards. I'll invite George to say a few words. The reason there are two of us is that while this program is administered in the ECE department in the Viterbi School of Engineering, it was conceived by a broader array of faculty from multiple schools, especially from Viterbi and from the Dornsife College of Letters, Arts, and Sciences, where George is. So, while administratively it's centered in engineering, the classes are in multiple departments, taught by faculty in multiple departments, and we accept students from multiple backgrounds. So let me bring up some slides. Okay, so the reason that we created this program in quantum information science is because the field is rapidly growing. So when I began working in this area, which is a long time ago now, it was largely an academic subject. The work in this area was mostly pure research. There were certainly some people in companies working in this area, but mostly on pretty fundamental issues. Theory had far outstripped experiment, let alone developed technology. But that has really changed in the last several years. And the first small quantum processors are here, what the so-called NISQ machines, noisy intermediate scale quantum machines. Several companies have developed these, including IBM, Google, Intel, IonQ and Rigetti, which are two startup companies. And in fact, because of the recent development in these technologies, a number of major companies have started making significant investments in this area. So I mentioned IBM and Google, Intel, they're all working on hardware. Microsoft has been developing software. Um, Amazon has been developing software as well, but this is by no means a complete list. And it's by no means only US companies. Alibaba and Tencent have both started quantum computing efforts. One of my former PhD students was hired by Tencent to start up their quantum computing effort. And then there are new companies, startups, who've been moving into this area backed by venture capital. Some of these have been around a while. Idée Quantique, which is based in Geneva, Switzerland, makes quantum cryptographic systems. D-Wave makes special purpose quantum optimization computers. One of their machines is housed at the Information Sciences Institute here at USC. Well, not on the main campus, but in the ISI facility in Marina del Rey. There's a company in the Bay Area called Rigetti who makes superconducting processors similar to the ones that IBM and Google have been working on. A company called Q-Control that designs control software to operate on quantum computers. They're an Australian company that has an office here in LA. Xanadu, which like D-Wave is a Canadian company. And a much longer list. I'll show you a not up to date list in a moment. So this industrial development has really started changing the field. It's moving, while research is still a very large part of what is done both in academia and in companies, there's a move towards commercialization, towards building bigger and more powerful processors, exploring their applications and reaching out to potential customers. So the opportunities for careers are growing as well, in research, of course, in the design of these machines, in their actual construction and operation, and also in programming them and developing software. So people are excited about quantum information for a variety of reasons. The field really took off in the 90s with the discovery that quantum computers could efficiently factor large integer numbers, which would make them useful for breaking crypto systems. That's a very demanding application, but one that the large-scale computers of the future will be able to do. But in the meanwhile, many other applications have been studied. Another early application was to cryptography. You can use quantum bits, especially photons traveling through fiber or through free space, to share secret keys for cryptographic purposes. Quantum computers, even fairly small ones, could be done for quantum simulation, simulating quantum systems, which is a very difficult problem for classical computers. Was one of the first anticipated applications of quantum computers all the way back in the early 1980s by Richard Feynman of Caltech. And other kinds of advanced computation are also boosted. One of the areas that people are most interested in is chemistry. Chemistry, in some sense, is applied quantum mechanics, and it's very difficult to do fundamental simulations with classical computers. So people are very interested in a variety of different topics in chemistry, developing new catalysts, studying protein folding, for developing pharmaceutical applications, and so forth. Another area is using quantum systems for optimization. There are certain types of optimization problems that, in principle, could be solved much more quickly using quantum computers. That's what the D-Wave machines are all about, is solving a certain class of optimization problems. There's a very exciting algorithm for solving large linear systems, which has a wide variety of applications, potentially in many different fields. Recently, there's been a lot of exploration of applying quantum computers to machine learning and artificial intelligence, where again, there may be boosts in the ability to train machine learning systems. An area that's at an earlier stage of development, but is a very exciting one, is in sensing and metrology and precision measurement. So one of our faculty members here, Susumu Takahashi, is working on developing sensors using what are called NV centers in Diamond. Another faculty member, Eli Levinson-Falk, does work on sensors using superconducting systems. A theorist recently joined the ECE department, Chuntao Zhuang, who does the theory of quantum sensing. Also, a new faculty member in industrial and systems engineering works on optimization. I should have mentioned him. And then there's a variety of other communication type protocols that use quantum systems for communication, for authentication of messages, and quantum signatures, secret sharing, and a number of other protocols. So this is a list I pulled off of the website of one of my colleagues here, Professor Daniel Lidar. He maintains a list on his website of companies investing in various areas of quantum technology. This list is actually quite out of date already, but you can see it's quite an extensive list, and it includes both large companies like Google, Hewlett-Packard, IBM, Intel, Lockheed Martin, and so forth, and also startups like Q-Control and Rigetti, Xanadu, and many others. So as an example of how rapidly things are growing, this last March, just a month ago, I was at the American Physical Society's March meeting in Las Vegas. The March meeting is, as far as I know, the biggest physics meeting in the world. And in their exhibitors hall, a large fraction of all of the exhibitors were working on different aspects of quantum computing. So I snapped a few pictures while I was there. These are all different companies that were trying to recruit people. They're trying to market their technology to researchers, and are a sign of how rapidly this field is growing. Right. So you've been admitted to the master's degree program. So what is required for this? So as I mentioned, the MSQIS is actually a collaboration between several departments here at USC, electrical and computer engineering, which is my primary appointment, the physics and astronomy department. I am actually a physicist by training, and a number of the faculty here working on quantum information and computation are in the physics department. The chemistry department, where there are other faculty, including Professor Lidar and Professor Takahashi that I mentioned, and computer science, where there are a couple of faculty working on different aspects of quantum computing. So for more or less administrative reasons, the program is administered in the ECE department, which is a very large and highly ranked electrical engineering department. It's hard to administer a program across multiple departments, so we made the decision to administer it there. But there are courses in a number of different departments that make up the MSQIS, and it's taught by faculty from multiple disciplines. So the requirements are 28 units minimum. And these are divided into 3 groups. So there are 3 foundational classes, which is 12 units altogether. Typical classes is 4 units. Then 7 or 8 units of what we call core, which would be basically 2 other classes chosen from a list of approved core classes, and then 8 or 9 units of elective classes, which are drawn from a very large list. Plus, we can approve other classes. The list is ones we thought students would be most likely to find useful, but we're very open to approving other technical classes as electives. So it can be done in 3 semesters. Some people, so we're now in the second year. So the first cohort are in their second year. Some of them have graduated in the fall, but some of them are taking 2 years. So either 3 semesters or 2 years are quite possible. The instruction is in person, and we expect people to enroll full time, though we do have a couple who are working, and therefore they're completing their degree over a longer time. During the pandemic, classes were online, but we've been moving back to in-person instruction, so pretty much all classes are in person. I have been doing my classes in person, but also on Zoom simultaneously, just as a convenience. But the exams are all in person and on campus. The emphasis is on the fundamentals of quantum information science with an eye towards being able to then apply them to practical applications. So ideally, someone could go from this degree program and go straight into a job at one of these companies. Or could apply to a PhD program and go on to get a PhD if that's more what you're interested in the academic route. So this is a pretty new thing. There are not very many master's programs in this field yet. I know a number of universities have been thinking about putting them. A few have started to actually put one together. There's one now at UCLA, there's one at Duke University. There are a few others around the country and around the world, but it's still a pretty new area as far as an academic discipline. The field itself is almost 30 years old, if you count from when people really started working on it intensively in the 90s. But it's only recently grown into the very large, widespread effort that it is now. So if you want the exact details of the requirements, you can go to the USC course catalog, which is online. If you choose the menu of programs and scroll down to the master's programs, it's under Masters of Quantum Information Science. Okay. So the courses that we give are a mixture of the theory and some practical hands-on applications. So we want everyone to have the opportunity to actually use quantum devices. In most cases, this is done over the, in the cloud, over the internet. The devices themselves often need very specialized equipment to operate, dilution refrigerators and magnetic shielding and all of that kind of thing. So if you take certain classes or do directed research with certain of our faculty members, you may be able to get even more hands-on than that with experimental systems. But everyone should have the opportunity to write and run programs on quantum processors supported by the various companies working in this area. Apply them to at least simple versions of real-world problems. So one of the classes that's required for this degree program is Physics 513, which is on programming quantum computers to solve problems. We'd like people to be able to come from USC and go into a position at one of these companies, either a startup or one of the established companies. To have the opportunity to use the software that's been developed. There are several different software systems that have been developed. IBM has a system called Qiskit. Microsoft has their own system. And finally, your professors are all faculty members who are active researchers in this area and support groups of PhD students and postdocs who also take these classes and do research in this area. And you'll have the opportunity to interact with these people as well. And hopefully, if you are interested in that, have the opportunity to do research yourself. We tried to make the degree program pretty flexible with a variety of electives and different choices for the core classes, because we hope to have students from many different backgrounds. So some students will come from an engineering background, electrical engineering perhaps, some will come from computer science, some will come from physics, some may come from pure mathematics or chemistry or many other disciplines. But those are ones that I know we've gotten students applying from. And the classes are designed so that students from many different backgrounds can receive the preparation they need. So here's some more details about the classes that make up the program. So the three foundational classes, which are required for all MSQIS students, are the class in quantum information processing, which is EE 520. It's usually taught either by myself or by Professor Ben Reichart in the ECU department. There's a class on quantum error correction, EE 514, which is taught by Professor Ladar. And then applications of quantum computing, physics 513, which I mentioned a moment ago, which is taught by Rosa Di Felice in the physics department and Ichiro Nakano in the computer science department. Then you choose two core classes from a list of approved ones. New classes are being created all the time. So we recently had a class created in computer science on quantum cryptography. That's now in the process of becoming a regular approved core class for this degree program. But while classes have not yet been formally added to the program, we can still approve them to satisfy core requirements if they're appropriate for that. Another one that was offered last year was a class in fault-tolerant quantum computing taught by Ben Reichart. So I approved that to count as a core class. We have a class that's being developed right now in the ECE department on quantum sensing that we hope will become a regular class in a year or so, but in the meanwhile could be approved to count as a core class. And then elective classes that can be in many different areas, not specifically quantum classes, but related to computation or to quantum physics. So among the other core classes, there's a class in quantum information theory, which I'm teaching right now. There's a class in open quantum systems being taught right now by Professor Ladar. There's a class in quantum devices. It's a physics class that will be offered in the fall. It's more about the actual hardware. And then elective classes in quantum mechanics, quantum chemistry, algorithms, cryptography, high performance computing, and information theory and data science. So a typical program might look something like this, but it's designed to be fairly flexible. So you would arrive in the fall. The best thing to start with is EE 520, Introduction to Quantum Information Processing, one of the foundational classes. And perhaps couple that with an elective class. So you could take a class, depending on your background. You might want to take a class in quantum mechanics. You might want to take a class in linear algebra. Linear algebra is heavily used in this field, so it's good to be very familiar with that. or a class in algorithms or something like that. Then in the spring, you might take the second foundational class, Physics 513, and one of the core classes, for example, Open Quantum Systems, and then perhaps a second elective. Over the summer, there are different options. A lot of students apply for internships with companies. So there are many companies that offer internships. It's a competitive process. So it's good to get applications out to a number of places. Some students have done summer schools. These are offered from time to time. Some students stay on campus and do directed research with a faculty member. And then in the fall, you could take the third foundational class, quantum error correction, and another core class like quantum devices. So this is a sample program. Exactly what electives you might choose will depend on your own background and also your interests, what kind of a career you want to go into, what kind of work you're interested in. And the order can be shuffled to a pretty significant degree. Okay. So if you have questions, we'll answer questions now as best we can, but you should also feel very free to reach out to us to ask questions if any occur to you after this. So my email address is given here and George's. Cami Lee is in the admissions office in Viterbi. She can answer questions about the program requirements and the nuts and bolts of enrolling and details of that kind. And she's certainly not the only one. There's a whole office of people in Viterbi who are very happy to assist you. All right, so thank you very much for your attention. I'm happy to answer questions, but perhaps before we get to that, I'll ask George if he wants to add anything.
No, I think you covered it perfectly, Professor Brun. The one thing I would just double down on in terms of the remarks you made is to say, obviously one of the most exciting parts of this degree is the emerging applications in the field and in so many different ways. And I think that's very much reflected, as hopefully you all received this impression from the remarks that Professor Brun made in the collaborative and interdisciplinary nature of the curriculum and the faculty who teach in it. I mean, I think among the faculty you referenced, there's faculty with appointments in computer science, electrical engineering, industrial engineering, chemistry, physics, and that is obviously plays into the ways that quantum information science can be applied in so many different fields, and the breadth of elective options you have as students in this degree, I think, sort of feeds into that as well. So we look forward to how you craft your education in this program, and also obviously your future careers beyond that. We hope that you continue to stay in touch and help to influence the direction that this program takes.
Thanks a lot, George. Yeah, I heartily agree.
So I do want to urge all of our participants that now is a great time to go ahead and start asking questions. If you could use the Q&A, the question and answer function for that, we'd really appreciate it. But I do have some initial questions that were sent in advance, so I'm going to go ahead and start with that. Some of these I know, Professor Brun, you actually already touched on, but we did get quite a few questions regarding what type of research opportunities are available within the program.
Yeah, so there are several ways that one can become engaged in research. So one of the elective options, and in certain cases, I have counted it as actually fulfilling a core requirement, which requires approval, is what we call directed research. So a directed research counts as a class. You sign up with a particular faculty member, so that requires obviously their agreement. And you sign up for a certain number of units of directed research for a semester, or sometimes people do it over a couple of semesters, maybe 2 units in one semester and 2 units in another. And you work on a project, a research project, under the supervision of that faculty member, sometimes often on your own. I mean, not on your own, just one-on-one with the faculty member, but sometimes perhaps in collaboration with another student or a PhD student or postdoc. So this can be in a huge variety of different areas depending on the particular faculty member. So if this is something that interests you, then a very good thing to do is to go and meet the faculty. You obviously can meet them in taking their classes, and that's a great thing to do. But you can go to their office hours and talk to them, ask them questions about their research. I would strongly urge you to not be shy, right? Office hour, many people think somehow coming to a professor's office hours is bothering them or something like that. But that is exactly what office hours are for. And they're not just for students taking a class with that professor. So if you want to, you can send an email to the professor, say, I'd like to talk to you, come by their office hours or make an appointment, chat with them about research. Generally, depending on your background, it's generally not that easy to plunge into it right in the first semester. So often you need to get take some classes and get some background under your belt. But some students come in, they already have some knowledge. Maybe they've done some work as an undergraduate, and they're interested in going ahead. So that's the main sort of formal opportunity. I'll mention another couple. Sometimes students don't want to take it as a class, don't want to take it formally as directed research. In a case like that, with the agreement of a professor, you can actually be a research volunteer, which is you're just working on it in your spare time. Otherwise, it's very similar to directed research. We do encourage people to do directed research, so you get credit for the work that you do. But sometimes people want to take more classes and want to try to fit research in on top of it, and that can be done. And then the third major opportunity is through an internship. So if you do an internship with a company during the summer, then that will often involve research on whatever projects that company is undergoing. So those are the 3 main possibilities. And we do encourage people, not everyone needs to do research, but those who are interested, we encourage you to reach out.
Great, thank you very much. So obviously a lot of students are thinking about careers, and we do have someone asking whether previous students, I know this is a very new program still, but they're just wondering whether most of the students in this program seem to be going on into PhD programs or directly into industry.
That's a very good question. It is still very new. So the first cohort of students were admitted in the fall of 2021. So they are just starting to graduate now. A lot have applied to PhD programs. Some have applied directly to industry instead. So both of those are routes that students have been taking. It's a little early to know outcomes, actually. because people who are applying to PhD programs are basically are applying in this academic year for admission in the fall. So I know some have gotten in to some schools. I don't know the full tally. I will say, while you can go into this program from a variety of different backgrounds, if you try to make too big a jump, that can work against you. So if you, for instance, have an undergraduate degree in computer science, and then you do this degree to jump into a PhD program in physics, for example, many physics departments might see that as a really big leap. So that can be a handicap. So you can't completely free yourself of your background, but I have known students who've done exactly that. And of my former PhD students, one of my PhD students was in electrical engineering. He's now a professor of physics at Cornell. So these kinds of shifts can happen, but it's something to be aware of.
Great, thank you. Kind of a follow-up for that. We have a student saying, I've heard that QIS is a very niche field, which may demand a PhD or strong research profile for jobs. So it sounds like the questions are like, realistically, do they really need to get a PhD to excel in the field?
So I think the answer is no. You don't need to get a PhD to work in this field. I mean, the whole point of this program was because there were growing opportunities for people without a PhD. For quite a while, basically all the jobs, well, not all, but almost all the jobs in the area required a PhD. They involved research, either applied or fundamental research, and that was true in companies as well as in academia. That is changing, but there are still a lot of jobs like that. So that is certainly one route, and still, a common one to going into a career in industry, is to get a PhD first. And having research experience with or without a PhD will almost certainly help you, because they want, in addition to the classes that you've taken, that shows that you can actually sort of do work in the area as well. So I would say, no, you don't need a PhD to go into the field, but that shift is ongoing, right? So there are still a lot of positions that do require a PhD. So some of it depends on what kind of a thing you want to do. Anyway, that was a pretty wishy-washy sort of answer, but it's a dynamic situation, so that it's changing, as we speak. So we don't really know what the mix is going to be a couple of years from now. We know what it was a few years ago, where it was almost all PhDs. So it's shifting, and how quickly, we don't know.
Perfect, thank you. Let's see. Do you happen to know, someone is asking, do you know the total number of students in the program and how many have been admitted for this coming fall?
So let's see. I believe that in the first year, we had 9 students actually enroll. And in the second year, fall of 2022, I think it was 15. I don't know how many students have been admitted. I received an update several weeks ago, and I forget what it was, then 30 something, or maybe it was more. But obviously, students are generally considering multiple schools and multiple different options. So we admit more than actually. So honestly, I don't know in the current group of people who've been admitted what the total is. Does
Yeah,
anybody
I
know that?
think I think the last number I saw was about 45 have been
About
admitted
45.
to this
Okay.
one.
Yeah, so I imagine that, I mean, that squares with what the number was a bit earlier in the process.
Yeah, I have a question here. I think ECE professors who are working in the QIS area are more on the theory side. Is that correct? If so, can you briefly talk about how is theory research different from experiment research?
Oh, that's a big topic. So yes, most of us are theorists in ECE. Actually, at USC, there are more theorists in this area than experimenters. Eli Levinson Falk in the physics department is an experimenter who does superconducting circuits and quantum bits and things like that. Susuma Takahashi in the computer science, in the chemistry department is an experimenter who does nitrogen vacancy centers in diamond. There's been some work related to this by a faculty member named Steve Cronin, who works on carbon nanotubes, and Michelle Povinelli. She's sort of partly a theorist, partly an experimenter. Anyway, she does photonic stuff. But yeah, we're more theory than experiment at the moment.
Okay, great.
Oh, I didn't answer what's the difference? Yeah. So theory, well, okay. So in theory, I mean, obviously you're working with mathematical or computational models of systems rather than working with the physical systems themselves mostly. This may be a purely analytical kind of work where it's more or less mathematical derivations, solving problems that way. It may involve numerical simulations on ordinary classical computers. It may involve some combination of these. So, there's also designing protocols and things like that. So that's theory. In experiment, you spend a lot of time, very carefully and meticulously setting up systems in order to take very careful measurements and things like that. Whatever kind of research you do, it takes a certain amount of immersion to get to sort of internalize the background that you need in order to make progress. So, one shouldn't be too impatient. A few people just jump in and swim, and that, I mean, more power to them, but that is by no means the norm. And I should also say, there, what you count as experiment is actually sort of a sliding standard right now, because there's a lot of hardware that's accessible through the cloud. So you're not actually putting your hands on it yourself, but increasingly people are running programs on quantum processors of various kinds. We have the D-Wave machine here at USC, but there's also access to the processors at IBM and Rigetti, and Honeywell has a collaboration with my colleague Daniel Lidar. So they have an ion trap based quantum computer. The startup IonQ has a machine like that as well. I forgot to mention Honeywell earlier because they've really grown in the last few years. They've spun off a whole new company called Quantinuum, which is building these machines. Last I talked to one of the people there, they had like 200 employees already. It's pretty amazing how quickly this is changing. Wow. Anyway, hope that gives you a bit of a flavor anyway.
Thank you. A more academic question. Someone is saying it appears that the program is very physics focused. For someone without a physics background, do you have recommendations, or are there any required prerequisites?
So no, there are no required prerequisites. All of the classes, all of these foundational and core classes introduce the physics that you need to take the classes. So EE 520, the first part of the class is a review of those aspects of quantum mechanics that you need to do quantum computation and information. So we do not expect that everyone who comes in will have taken a quantum mechanics class. They don't have to be have a physics background. We have people from computer science who've never taken a physics class. That said, if you have taken a physics class, that can be a real benefit for certain things. So for quantum sensing or for quantum devices, the kind of quantum mechanics that you would learn in a physics class is helpful. In quantum computing and information, we teach you the background that you need to know.
Great, thank you. So someone was curious, and I know we do have some, but if you could elaborate, does USC have partnerships with players in the quantum industries? And do they help with finding internships and professional experience?
Well, we try to help. We do have some connections. Some individual faculty have collaborations with some of these companies. So Professor Ladar has ties to D-Wave and Google. Professor Reichard is doing research at Google. Professor Levinson Falk has ties to Q-Control. Professor Di Felice to Xanadu. So there are some connections like that. We will write recommendations and try to make connections as far as internships go. Also, you know, as mentioned at the beginning, the Career Services Office at Viterbi can give some help, both in looking for a job after your degree and also in applying for internships, you know, some of the nuts and bolts aspects of it in particular.
Okay, thank you. I know you had mentioned 3 primary ways that students can do research within the QIS program. Someone did ask whether it is possible to do a thesis as part of that program.
So we don't have a specific thesis option for the MSQIS. No one has done so far, and most of the MS programs in Viterbi don't have a thesis. That said, in principle, there is a class in EE, which is the master's thesis class. And I don't know a reason why an MSQIS student could not enroll in that class and do a thesis. To do that, you would need to have a thesis advisor. So you would need to have someone who would agree to supervise that process, and a committee that would you know, read the thesis and pass it. So and like I said, most MS students at USC don't do a thesis, and we haven't created a specific one MSQIS option for that. So it hasn't really arisen, but I think it's probably technically possible to do.
Great. So someone is asking, and I know you've actually talked a little bit about this, but someone is asking just sort of what are some of the current research directions in quantum computing?
Yeah, that's a great question. It's a fast-moving target. So here at USC, people are doing research in a bunch of different areas. So quantum error correction and fault-tolerant quantum computing is a big area here. What's called dynamical decoupling was pioneered by a couple of our faculty here, Professor Ladar and Professor Zanardi. That's a become a major part in how people are trying to build better quantum computers. Quantum simulation is an area. So Professor Di Felice works on that, Professor Nakano. Some work on algorithms from Professor Reichardt. I've done work on some algorithms, quantum walks, quantum sensing of various kinds, both theory and experiment. I mentioned Professor Levinson Falk, who works on superconducting quantum processors. Gosh, let's see. Those are ones that occur to me off the top of my head. I mean, it would be a lengthy list if we listed everything that all the faculty work on, because most of us actually have a number of different, strings to our bow. So there's quite a variety, and it's changing all the time because the field is changing.
Great. Actually, since we only have a couple minutes left, I'd like to ask Onkar, one of your students, to open up his video, and if you could just kind of tell us a little bit about yourself and why you chose this program.
Yeah, so I'm Onkar. I'm from a small town in India called Badlapur, and the main reason I chose USC because I was mainly interested in theoretical work, and USC seemed like a good fit for me. And another reason was breadth of course choices that you have. As Professor have already mentioned, you apart from the foundational courses, you can take courses from math like applied linear algebra, applied probability, CS courses such as algorithms, some chemistry courses, and you can even take semiconductor and fabrication courses as well as hardcore physics courses like advanced quantum field theory. So you can really tailor the degree the way you want. So that was one of the major reasons why I chose USC.
Thank you very much. And because I know it's always a big question for students, can you tell me a little bit about your housing situation and how you found it?
I looked at the online websites like apartments.com and Zillow, and then I choose the apartment which I like the most. And then there were several Discord groups and Facebook groups where I connected with people and asked them to be roommates, and then I signed lease for the housing.
Great, thank you so much. Looks like we're just about over. I'm going to go ahead and put my email address in. So just in case you did not get your question answered during the session, please go ahead and feel free to email me, and if I can't answer the question, I am happy to forward it to an appropriate person to answer the question. Thank you all so much for attending our information session, and many thanks to Onkar, Professors Todd Brunn, my colleague Maria Sandone, and Professor George Ingersoll for basically helping us put on this event. And again, thank you so much, and fight on.
Thank you.